እንችላለን። So this is chapter 2. It is about compressible flow with friction and the heat. And under this chapter, we are going to study the some important topics which are related with aerodynamics, not only aerodynamics, but thermodynamics. And the principle of thermodynamics works in the aircraft propulsion system. Therefore, the study of propulsion is intimately linked to understand the internal fluid mechanics. Okay, so this internal fluid mechanics means the flow that takes place through the duct. Okay, duct flows are the primary interest to the propulsion because the flow through the combustion chamber is related with duct flow. And the physical phenomena in the real ducts includes the friction. There is friction due to the presence of fluid flows through the duct. There is also heat transfer because we in the combustion chamber, fuel and oxidizer or the oxidizer from atmosphere comes from outside. The fuel is from the fuel tank will be mixed and they produce high temperature gas. So heat transfer that take place through the walls. Again, the chemical reaction that the fuel and oxidizer mixture performs chemical reaction within the combustion chamber. So that is one thing. Again, there is also area variation that the combustion chamber contains some convergent, divergent nozzle and other things, so that area variation also is there. The compressibility effect. This is the compressibility effect is related with density variation. As the gas compressed, it is density change. So at high supersonic flow, the gas is considered as a compressible fluid. And whenever there is a compressibility effect there is an appearance of the shock waves. Maybe it can be oblique shock wave or it can be expansion wave or it can be any type of shock type. Therefore, we'll see all the thermodynamic phenomena that take place within the combustion chamber. So the first thing is the law of thermodynamics. So I don't know how much of you are familiar with thermodynamics. So it needs some revision on thermodynamics. Anyways, the law of thermodynamics governs the relation between the state variables. And these state variables in our discussions throughout this chapter are density, pressure, absolute temperature, the entropy, the internal energy, and other derivative properties. Among the derivative properties, enthalpy is the one. So H is enthalpy, and also specific constants. Okay, specific heat constants, like a specific heat at constant pressure and a specific heat at constant volume are the derivatives. So this about 5 or 6 variables like density, pressure, temperature, enthalpy, internal energy are the 5 the flow field variables or state variables, we call them. So they are throughout in our discussion, these variables are there. So in addition to the law of thermodynamics, the fluid flow problems need some conservative principles like mass principle, mass conservation principle, momentum conservation principle, and energy conservation principle. Okay, so it obeys conservation principles. The conservation principles are 3 types. One is mass conservation, another is momentum conservation, and the third one is energy conservation. So this 3 conservation principle gives us 3 equations. And in addition to the 3 equations, we need more 2 equations. So one of the equations obtained from the derivative properties And another one is obtained from the gas law, the perfect gas law, or the Boyle's law from your chemistry. So combining these three equations with the two derivatives and the state equations, we can solve the problem that are related with 5 unknowns with 5 equations. If we have 5 unknowns, then we must have 5 equations in order to solve or to be determinant. Okay, so that is what. So when we come to the review of thermodynamics, in gas turbine engines, the medium is perfect gas because our gas is air. Air is considered as a perfect gas. And the perfect gas law relates the pressure, density, and absolute temperature of the gas, which may be derived rigorously through the kinetic theory of gas. As I told you, these three quantities can be described through the energy conservation principle, mass conservation principle, and momentum conservation principle. And during solving these equations or during finding these constants, not constants, but field variables, we have to use some assumptions. Among the assumptions, one is the intermolecular force between the molecules are negligible or they are considered small, so that we don't consider the intermolecular force. So the molecular theory, which is microscopic theory, is not applicable in our case here. Again, the volume of the molecules that occupy space is considered very small. So these are the two assumptions for our next work. So these two assumptions leads us to have the perfect gas law. The perfect gas law, or the state equation, we call that pressure is equal to density times gas constant R times absolute temperature T, is the what we call the state equation. This state equation is one of the equations for our next discussion. So here the gas constant is given 287 joule per kilogram Kelvin. That is for air only. For other gas, it is different. Then the specific heats at constant pressure and volume are also be found from the thermodynamic relations. So the perfect gas in terms of specific heat at constant pressure and at constant volume, DH is equal to Cp. Cp is specific heat at constant pressure. And dT is the differential form of temperature. And DE indicates the internal energy. So DE is equals to CV dt. These are the two equations again from the perfect gas assumptions. Again, the specific heats at constant pressure and volume are a function of gas temperature. As you see, they are a function of gas temperature. So Cp is equal to Cp of T and Cv is Cv of T. Just this is a function actually. So Cp is constant, Cv is constant. So for calorific perfect gas, we have Cp and Cv, which are constants. So actually, this is just simply how we can calculate some thermodynamic relations from the perfect gas law. So calculate the density of dry air where it is static pressure and temperature are given. Actually, static pressure is given 3 megapascal. That means 3 times 10 to the power of 6 Newton per meter square. Temperature is 25 degrees centigrade. Then required density.